In this video, I'm also going to talk about which algorithm gives you a better accuracy. Just using polynomial regression, the complex algorithm may not give you the best accuracy. And we're also going to see the demo on these algorithms so that you will get the best insights of these algorithms and also understand how they work. So make sure to watch this video till the end. Now let's jump to the third part, that is polynomial regression with one variable. It is again one variable, but the name is polynomial regression. It is not linear regression. Let's understand what is polynomial regression. The question here is why I should use a linear regression only? Why I should think of drawing only the straight line? Why not to draw a curve that fits better on the data, right? Though the nature of the data is linear, I may not get the better accuracy if I use the straight line. Why not to think of drawing a curved line, right? And that curve is nothing but polynomial regression. So if my line starts taking the curves, then I may get better accuracy, and that is going to be my polynomial regression, and that's where my accuracy will drastically improve. As you can see, based on the number of iterations, the best fitting line is getting drawn on the data, where it is just a straight line, and in case of polynomial regression, it is trying to fit the curve on the data. By looking at this graph, you can easily say that the curve would be the better fitting line over the data rather than the straight line, single straight line, right? Alright, so what is simple polynomial regression? The best fit line is not a straight line, rather a curve that fits into the data points. A best fit line may not be the straight line always, it can be the curve rather that fits on the data points. So even straight line with multiple features may not give us the best accuracy. This is what we have seen. That the change in the accuracy is not much. The accuracy that we have got with simple linear regression is around 82%, whereas in multiple polynomial regression we got around 83%. So no much difference. Then that's why we can think of drawing a curve rather than drawing a straight line. That may improve the accuracy. Okay, but again I'm saying simple polynomial regression. Simple stands for again one variable that we are considering. Consider only one input variable to best fit the curve on the data points, and hence we are calling it as simple polynomial regression. This is the data that we need to prepare for simple polynomial regression. If you check, we have only one column which has been given, that is size of the house in the square feet, which is x1. What are other columns? If you observe other columns, x2 and x3 are the same column, size of the house in the square feet. They are not different, size of the house in the square feet, size in the square feet, size in the square feet. The columns are same. The only difference is they are getting squared. We are increasing the degree. The second column is 300 raised to 2. The third column is 300 raised to 3. And the fourth column is 300 raised to 4. So we are just increasing the degree here. That is what polynomial regression. So to take the curve, we need to increase the degree. When I say increase the degree, that means you are squaring, you are cubing, you are increasing the power of that feature. Only this is the extra step that we need to take care in case of polynomial regression. We need to increase the power of our features. Don't worry about the math behind polynomial regression. We'll discuss the math behind polynomial regression in some other video. Let's jump to the demo part now. Alright, polynomial regression with one variable. I'm importing NP, sklearn preprocessing, polynomial features. Why I'm importing this? Because I told you the extra step that we need to perform is increasing the degree, increasing the powers of the features that we have got, so that the line starts taking the curve. So we have prepared some function which takes degree as parameter again, where degree is nothing but the input parameter that we are gonna give, and that means where the straight line starts taking the curve. Degree 1 is nothing but your straight line itself. Degree 2 is where your straight line will start taking the curve, right? As you increase the curve, then better is the accuracy. How? Let's see that. We have again prepared x and y here, nothing different. It is just one feature, one variable. Okay, nothing different. Again, it's the same algorithm, linear regression that we have prepared. Regression.fit x and y. And the additional step that we have to do is x quadratic. That means I have to increase the power of the x column, that is x square, x cube, x raised to 4, x raised to 5, and so on. right? To increase the power, I need to prepare x quadratic. So I've used polynomial features, the inbuilt library, to increase the power here, and I have prepared x quadratic. It is just a variable. You can provide any name to the variable. Alright, and then finally we are just training our model. If you check, I'm doing x quadratic dot fit, right? It is not x only, it is x quadratic. The input having some power, right? Whatever degree you're gonna pass, if I pass degree 2, then the square of this 300 will be passed as x quadratic, right? So I'm passing x quadratic and y will remain same. And these are not simple x and y, okay? This is x quadratic and y. And here we are just plotting our data and line so that we can check how it looks like. This is what we have already discussed. Here I'm using matplotlib plt plot xy, and I'm x column, y column, axis, grid, scatter plot, and plot.show. Let me execute this as well. This cell contains interact functionality again. This is again IPython widget where I'm calling polynomial regression function, and the degree between 0 to 10, I can change the degree. As you can see, when we have degree 5, the residual sum square error is 377.28. Amazing. The error is decreased drastically. When I am saying degree 1, you can see in the graph below, right? The degree 1 is nothing but linear regression, the straight line. When I change it to a degree 2, this is where your line will start taking curves, and you can see just by increasing degree by 1 point, you made degree 2, and the accuracy is improved, and the residual sum square that you have got is decreased drastically. This has become 544.62 on degree 2 itself. You can easily compare this now, how drastically the accuracy is increased by using polynomial regression, right? So let me note it here. The third type that we have used is a simple polynomial regression, and the accuracy that we have got on the trained data is this. This is residual sum square error. You can compare the accuracy. You can compare the error in simple linear regression on trained data is 2818. On multiple linear regression is 2759, and in simple polynomial regression it is drastically decreased to 544, where degree you kept as 2. When degree 1, that means a straight line. When I increase the degree, that means this line will start taking curve. You're increasing the power of the coefficients. We'll understand the math behind this, by the way. Okay, so the question is, why should we stop at degree 2? Let's increase the degree more. So if I make it degree 3, my accuracy is still better, and you can see this in the graph even. Why should we stop at 3? I've increased degree to 4. You can see now the curve is trying to pass through each and every data point. See, each and every data point it is trying to cross through, and this is where I got my best accuracy, that is 377.91 at degree 4. So let me note this also down here. Yeah, this is on degree 4. On degree 3 we didn't see much change, so I'm noting down degree 4. Again the accuracy is improved. And then why should we stop at degree 4? Let me increase degree more so that I can get the better and better accuracy. We want to reduce this error. This is error, right? To improve accuracy means I need to reduce this error. If I increase this more, you can see there is no much change. It is still 377. Let me increase more. Oh, as you can see, if I increase degree more, the error started increasing. On degree 6 it become 410. On degree 5 it is 377. Degree 6 it is 410. On degree 7 it is increased, right? As you can see, the curve is trying to pass through each and every data point here. But do you think that increasing degree blindly will improve the accuracy? No, right? That doesn't make any sense. If we keep increasing the degree, this curve will start taking sharper and sharper and sharper turns. The more sharper turns it takes, the accuracy will be better on the training data. But think of in the reality, think of this on the test data, right? See, I've increased degree to 8, more error now. So you need to study more, you need to think and understand what is the degree that is best suitable, what is the best balance that I can find, and where should I stop, right? In our case, we should stop at degree 4, 5. So at degree 5, I'm getting the least error, that is 377.28. Let me note this down here. Okay, and this is degree 5. This is the least accuracy that I've got, but this is again on trained data. Okay, I hope this makes sense. Increasing the degree is nothing but taking the sharper and sharper turns. Degree 1 is a straight line. Degree 2 start taking curves, and degree 3 is start taking more sharper turns. Degree 4 is start taking more and more sharper turns. So at some degree we should stop wherever we are getting least error and better accuracy. Let me test my model on the test data now. This time we are using test data, x test and y test, and on x test and y test we are going to predict. Okay, I'm just calling quadratic on prediction, the same thing. I'm not using model.fit again on testing data. Alright, testing data is the new data that we are providing to the model. That means we are just trying to find out the residual sum square error on the testing data. Let me execute this. Perfect. So when I check model.score on the test data, it is 8000211. Let me check the residual sum square error when I increase the degree here, right? So when I increase the degree, as you can see, when the degree is 1, the error on the test data is 3041. Isn't it the same that we have got in the linear regression, right? 3041 on test data. Let me note it here. So I'm saying error on test data 3041 at degree 1. Degree 1 is nothing but linear regression only. You can compare that. In simple linear regression on test data we got 3041. This is the error that we have got, and in simple polynomial regression test data at degree 1 we got 3041. Okay, now let's increase the degree. Increasing degree, straight line will start taking curves. So let's observe the error. This error is on test data, not on trained data. As you can see, as I increase the degree, error is also increasing. Error is not reducing, error is increasing. Okay, so this is not always the good practice to keep increasing the degree. So we should find the balance between wherever we get the minimum errors. Currently we have minimum error at degree 1 only. So it sounds like we should not go for polynomial regression then. Whereas the model is performing really well in home, but my model is not really performing at the client side. On the client data, on the test data, it is not really good. Okay, let me note this as well. So at degree 2, 4311 on test data itself. Okay, 4311.84 and at degree 2. So as error is increasing, we should not increase the degree. The best degree that I can see is degree 1. So this means what? Polynomial regression may not be good always. A simple polynomial regression at least for now. What is the conclusion from this? As I increase the degree on trained data, my error is decreasing, that is accuracy is increasing. On degree 5 I got the best accuracy, but as I start increasing the degree on test data, my accuracy is reducing drastically, right? So increasing degree doesn't make any sense here. So from this we can conclude that still we have a multiple linear regression is better, where we are getting better accuracy on both training and testing. Alright, let's proceed now. So if a curve with one input can give me better accuracy than the simple linear regression, then why not polynomial regression with multiple variables? Don't you think so? What I'm saying here is a curve, that means a polynomial regression with one variable is giving me a better accuracy, right, than the simple linear regression. Now why not to consider multiple features with polynomial regression? I'm using polynomial regression, but now not simple polynomial regression. I'm going to use multiple polynomial regression. I'm going to use number of features. Why to restrict ourselves to use only one variable? It's same like multiple linear regression. The way in multiple linear regression we have used multiple features but straight line. Now we are using number of inputs, different features, and along with the curve. So that may be the best algorithm that we can think of using here. So let's see our last algorithm here, that is polynomial regression with multiple variables. Now we are drawing a best fitting curve over the data points considering more than one input variable, x variable. Fitting a curve considering other factors like number of rooms or age of the house or status of the population living in that area. Right? In short, we are considering more than one variable, one input, that is cost of the house is not only dependent on the size of the house, cost of the house is also dependent on the number of rooms, it is also dependent on the age of the house, it is also dependent on some more features. like population living in that area, right? Along with that, I'm using polynomial regression. That means not straight line, start taking curves. And yes, these are the equations that is used to draw a line, best fitting line over the data. We already know in simple linear regression, it is y is equal to theta 0 plus theta 1x, y is equal to mx plus c, drawing a straight line, right? In multiple linear regression, this is the equation. In simple polynomial regression and multiple polynomial regression, this is the equation. Forget about this for now. We'll see this in some other video. What is the math behind polynomial regression, that we'll see in some other video. Let's jump to the demo part. We're again preparing x and y column in x, where we have size of the house and number of rooms here, right? More than one column, x1 and x2. Okay, but this time I'm gonna use multiple variables but polynomial regression. All right, let me execute this. We have a one function which is created, polynomial regression, mul polynomial regression, and we have a parameter that is degree. We need to pass the degree. So based on the degree, it should calculate the sum square error here, right? And based on the degree that you are gonna pass, degree 1, 2, 3, whatever the degree is, we are calculating x quadratic, and we are training our model. I'm using model dot fit here on x quadratic, not on simple x. Okay, not on simple linear x. We need to do it on the quadratic, that means squaring the powers. Okay, and finally we are calculating the error, that is residual sum square error. So as I can see, at degrees 1 I have 2759, which is same like multiple linear regression, right? 2759, 2759. As you can see, it is same on trained data. Okay, because we consider two features there, size of the house and number of rooms. Degree 1 is straight line, right? And this is what the accuracy that we have got in multiple linear regression. So degree 1 is straight line. Let me increase the degree. Amazing, amazing. As you can see, just at degree 2 the residual sum square error is drastically decreased. It is 271.87. let me note this down. On multiple polynomial regression on trained data, I got this accuracy. Residual sum square error is 271 on degree 2, right? So this is the best accuracy that I have got still now. It is better than polynomial regression, better than simple polynomial regression. We considered only one variable, right? So that's why we went ahead, one step ahead, and we considered more than one features. So the accuracy is way better than the algorithms that we have used till now. Let me check the accuracy on degree 3, 4 now. Oh, this is surprising. Can you see that? On degree 3 we got residual sum square error 0. On degree 4 we got 0. On degree 5 we got 0. Isn't it surprising? On degree 3 I got 0. That means 100% accuracy. That means your model is 100% accurate. Is it possible? That means, say for example, you are providing a new data to the model. You are saying 1000 square feet house and 3 rooms in the house, and you are getting 100% accuracy. In reality, whatever the cost of the house is, that is actually matching with the prediction that is been given by this model. Is that possible? Need to think, right? So should I increase the degree? The answer for this you will get in the next video, because we need to understand overfitting, underfitting and regularization. We'll see this in the next video. Okay, the last thing now, let's check the test error on polynomial regression with multiple variables. I've prepared x test and y test, the same data again, the testing data again. This is different data, testing data. Okay, and this time I have not created any function. We just have polynomial features, and degree manually we have passed. Degree is 2. Okay, so let's see what is the residual sum square error that we are gonna get on test error on degree 2. Okay, alright, so we got residual sum square error as 3827.94. Oh, this is really huge. And if you check at degree 2 in polynomial regression with multiple variables, on trained data we got 271. On test data we are getting 3827, which is really bad, right? And if I start increasing the degree, my error will also increase. Let's try that. If you remember, on degree 3 itself I got 0 error on trained data. If you check the same on the test data, at degree 3 I'm getting really high error. So this means increasing degree may not always help. When you increase the degree, The training error may reduce, but the testing error may increase. And this is where we need to find the balance between selecting the degree or making the curve to stop taking the sharper and sharper turns. We need to make it more smoother, more linear, and not sharper and sharper turns, right? So we want to stop the degree at some extent, and where to stop and which degree we should finally decide to get the best accuracy in training as well as in testing. That the testing accuracy is definitely the one thing that we should always look at, right? Alright, that is it for this video. See you again in the next video. Till then, take care and bye-bye.